that has too many wings, right? Yeah, it does, because it has 2 wings, and that's too many for me. How do we get here? Technology, that's how. How did the technology work? I don't know, but I'll tell you how the structure worked later. So first, when first airplanes started invented, you got the Wright brothers, I don't know why I did that, and their little Wright Flyer. That's not it, but that's a biplane, because it had 2 wings like the Wright Flyer. They had 2 wings because they just didn't have the structural components necessary for the single wing. So they had 2 wings because actually like kind of a structure element in its own, because the top wing kind of like helped support the bottom wing, and then kind of vice versa. There's little beams here, some wires to prevent, I think, like shear and torsion and collapsing of the wings and that stuff. There's a guy there, he's in the plane. Not in there, because it's another different drawing. Technology, this is like the 1910s, 1920s and stuff. This is around the 1930s, technology happens. And we got a wing. And that happened because technology, and we will go into why the technology made it happen is because we had better materials, and the better materials made it possible for the one wing, monoplane. Yeah, so basically, you got an airfoil, right? How do you support the airfoil? I don't know. So you got little thingies here. You got one big one, so you have the spars, and you have the outside, that's the skin, and okay. Skin on this one is fabric. This is metal. Actually, there's some of the fabric. The first one was the Hawker Hurricane. That's in our report. That had fabric skin because the British were backwards people. Monowing. One of the things about the monowing, it is basically the main structure of the monowing is we have the technology and materials to eventually make it stronger. So you got that big beam. Sometimes there's 2. Personal preference, I like 1. They're called spars. They basically take all of the load. Think of it as like a cantilever beam. Also running with it, you got stringers. Those mainly show up in stress skin, which is available by Anthony. Which was available now that we had like basically sheet metal able to become on the wings instead of fabric, because fabrics are nice but flawed people. Also, you got the ribs. That's kind of like the vertical stiffener. And like, the stringers are longitudinal. There's a guy in the plane. It's irrelevant. I guess we go to the equation. So basically you can think of it as a cantilever beam. What is a cantilever beam? It's a beam that's kind of supported on one end. It's kind of like just there. So main forces, well, I mean there's forces on it, but it's a moment. You got moments because there's a distance, and a moment is a force times a distance. Really don't have to explain that much. It's boom, it causes bending and stress, a lot of other stuff. Also, you got the airfoil itself, because like there, it's an airfoil, but it's not great, You know what's great? Not that airfoil. That's an ugly one. I guess it's not going away. Airfoil over here. And so basically it's got to support itself. So now the skin itself is carrying some of the stress. Because the wing here, that's pre-aerodynamic. The wing here, that's structural stuff. So you got cells, because you basically have like stringers here, vertical stiffeners, stringer, you get the idea. And this is a cell. So when you have basically forces or torques or anything in this cell, well, it's going to act over the entire thing. So first of all, you got the shear flow, basically the shear, that's Q, goes from string to string and stuff. That's equal to stress times T, I think that's right. Then you got torque equals 2Q A bar, which is A bar is it's basically for one cell. If you want to have basically this is 1, 2, 3, 4, 5, 6 cell. So you basically keep doing this until you get the idea. That's the torque, relates to Q, like shear stress. And then you got the twist rate, which is basically twist rate per unit length. You probably know that, maybe you don't, I don't know. That's 1 over 2A bar G. G is the shear modulus. and times the surface integral of basically whatever the cell is. So you could have a bunch of these. So basically, if for just one cell, that'd be whatever, Q T ds. All right, a shocking surprise. I got that right. Yeah, so basically, another thing is you gotta constrain it. So if cell 1 is rotating by a certain amount, cell 2 also has to rotate by a certain amount. So does cell 3 and cell 4. So basically, it's got this continuity. So in order to solve these equations, you basically just relate each one to each other. Do a bunch of different things. And what else can we do? That's looks like a tape wrench roll. Okay. Hey. Transverse shear. You got shear stresses. You got a shear stress over here and that stuff. Embarrassing.
The dimension seems kind of bad on that.
So that's Q. When you have a bunch of cells acting like this, you can cut those cells, cut those cells, cut those cells. So basically you're going to solve, basically this is 1, this is 2. Q1, 2 prime, and then you solve for Q naught. Basically Q of
This.
VZQ
Q over
IYY. I was mistaken. Or Q
equals ZC.
A. Yes, AS. So basically each cell. You do that a bunch of times, solve for the shear flow, that kind of stuff. And then that's